Okay, we're going to roll this real quick. Here's our digital replay, and today we're continuing our conversation about the ice ages by asking why? Why did they happen? Because if we understand why, maybe we'll understand when, right? It's just a thought. Okay, so there's lots of different theories about why the ice ages happen, but we focused in class and today in this digital replay specifically on Milankovitch cycles. And that's one word, Milankovitch. I just couldn't fit it inside the circle that represents Earth because it's a big name, Milankovitch. Anyway, so Milankovitch cycles, and this is going to be easier to explain if I switch to Doodle Mode. So I'm switching over to Doodle Mode now. So for this first Milankovitch cycle, or first astronomical cycle, we'll think of the orbital plane being this brown line here. And we'll put Earth on this orbital plane. Now, I'm really terrible at drawing circles, especially while I'm talking, so I'm just going to draw this circle. Hey, that's pretty close, but what are you going to do? Now, solar radiation is going to come at the Earth kind of like this. So notice that we're also looking at how much solar radiation we're getting at certain times. And the line perpendicular to the orbital plane and perpendicular to the solar radiation would be like this. And again, that's the line perpendicular to it. But that's not the axis on which Earth turns. And you've learned this before. You've learned this in elementary school. You've learned that Earth is actually tilted. And so I'm going to draw now the axis here that we rotate around, or Earth's orbital, or excuse me, rotational axis. And it's noticed that it's tilted from perpendicular. So it's not straight up and down like this line here, but it's tilted away from it a little bit. And it's actually tilted away from it about 23.4 degrees. 23.4 degrees. Now, that tilt is actually what causes us to have seasons. We have seasons because of that tilt, and the tilt changes from about 22.1 degrees to about 24.5 degrees. So it tilts that much, and that tilt causes the seasons because different parts of the Earth get different amounts of solar radiation, or different strengths of solar radiation, and we call this obliquity. And the cycle length is about 41,000 years. To sum it all up, that's tilt. Tilt is what causes the seasons. Tilt is the angle of Earth's rotational axis relative to the orbital plane, and it does have a significant impact in the change of solar radiation, even though it doesn't change the tilt that much. The tilt is really only changing a teeny tiny amount. Here's a nice little animation to show you. Every 41,000 years we get this little change in tilt. And when we graphed it, or when we looked at the graph of tilt, this graph B, was the more accurate depiction of tilt because the cycle of this little wave here was about 41,000 years or so. Okay, this if we imagine the x-axis to be thousands of years. About 41,000 years to make one cycle. So the next one, we're actually going to think of the sun and Earth as how they relate to each other. So in the next one, we've got the sun at the middle, and then we're going to have the Earth orbiting around the sun. Now, most people, when they think of Earth's orbit, they think of it as a circle. So again, here I'm going to draw an amazing circle, right? Because I'm so good at drawing circles. So here's my circle, my circular orbit of Earth, and there's my Earth there. So let's label the parts of our diagram, because you should label the parts of your diagram, especially when you're trying to teach somebody something. So here's Earth, and here's the sun. Okay, so there's the parts of our diagram. Now, Earth's orbit is not exactly perfectly circular. In fact, it's sort of elliptical. And it changes in how elliptical it is over time. So sometimes it's really elliptical, like this really horrible ellipses that I've just drawn while talking. And sometimes it's more circular. But always it is somewhat elliptical. It's not perfectly circular. And we call this the eccentricity of the orbit. Notice that at some points of the year, in the extremely elliptical one and in all the elliptical ones, at some points in the year, it is much closer to the sun than at other points of the year. So notice that the ellipses has a shape that makes it so that at some points of the year, the Earth is much closer to the sun, giving it a much higher concentration of solar radiation, or more solar radiation at those points of the year. So if you have this, you have a much bigger difference in the seasons, right? You have very hot and very cold. So this is another cycle. This is a cycle called eccentricity. This is another cycle which could possibly contribute to these ice ages, because the more elliptical it is, the more dramatic the seasonal changes, and the more circular it is, the less dramatic and the more availability for ice buildup. That's eccentricity. Eccentricity happens every 100,000 years. It's the shape of Earth's orbit around the sun, how circular or elliptical it is. So here we have a nice animation to show you some nice differences between the circular, which is what we're more like now, and the elliptical, which will be 50,000 years from now. When we were looking at the graphs, it most closely correlates with graph A, which takes about 100,000 years to complete one cycle of this wave. That's graph A, and that's eccentricity. Now, the third one is a little bit less intuitive. It's hard to kind of think about, but I'll try to explain it the best that I can. So in this one, we're going to again be looking at the Earth and its orbital plane, and we're going to again be looking at the tilt. Sorry, trying to draw a circle and talk here. We're again be looking at the tilt of the Earth and what that axial motion does. So we've looked at the fact that the axis tilt changes. So it changes from 23.5 degrees, and it changes back and forth in its severity of tilt. And now we're going to look at the solar radiation coming in. We're going to look at that tilt when it's in that angle. It doesn't just stay there. It's going to rotate. It's going to move. Now, this is different than the rotation of the Earth, because the Earth is rotating, but it actually will rotate around that little point that it's pointing to. So let's see if I can draw this here. It'll actually rotate around, so it'll be pointing to a different place in the sky. Right now, we're pointing at a star called Polaris. We call that the North Star, right? And eventually, we won't be pointing at the North Star anymore. We'll be pointing at a different star. But the tilt will still be the same. So the distance, the circle's radius that we're making this big circle, the circle's radius doesn't change here. We're not talking about the change in the angle, but we're talking about the change in where that thing is pointing. So here, if I have this little Earth down here, and I have the axis that we're rotating around right there in the center, and if we move in this cycle, we're actually going to point, the axis is going to point to a different place. And this is really hard to explain, but if we go... Think about it like a top. A top wobbles. So that wobble, it's the top of the top is going to point to a different place along that circle. Okay, so it's not it's hard to show on a static diagram. So let's go to a visual here in a second. But we call this precession, and it takes 21 to 26,000 years or so. So this is precession. That's precession. Precession takes about 20 to 26,000 years or so. It's the cyclic motion of Earth's rotational axis. It's like a top wobbling. Notice how it draws that nice circle in the air, just like that. That's precession. It most closely correlates with graph C because, again, it's about 20,000 years or so to complete one orbital cycle. So, where do we go from here? Well, if we composite them all together, we add all the graphs together, we get some squiggly line like this. So we know all three of these things are happening at the same time. And so if we add them all together, we have this shape of a graph that looks like this. Now, this is only 150,000 years if we consider this being the 1,000 years being the x-axis. Excuse me, getting ahead of myself here. But we have some data from the cores. We have some data from the little foraminiferas and the oxygen 18. So I think it'd be interesting if we expanded this graph to look more like the 650,000 year, same as the ice core data. Okay, so here is the expanded version of the graph. Now, I'm going to overlay, on top of this graph, I'm going to overlay our ice core data, which we've already analyzed and we already know shows us global periods of warming and cooling. So I'm going to overlay that right on top. And just for a reminder, when there is more oxygen 18, so higher levels of oxygen 18 in the foram shells, this would be a glacial period up here. And down here would be an interglacial period, or a warmer period down here. So lower levels of the oxygen 18 would be an interglacial period, and on higher levels of oxygen 18 would be a glacial period. Okay, so now let's overlay one on top of the other, and let's see if there's any correlation between these two pieces of data. So the black line is the line we just made with all the different astronomical theories, and the blue line is our oxygen isotope data from the course. Now, check it out. Every time the black line goes low, we have an increased amount of oxygen 18. So the black line goes low, we have a glacial period. The black line goes high, we have an interglacial period. Low glacial period, high interglacial. Low glacial period, high interglacial period. So there does seem to be a correlation. Now it kind of falls apart as we go farther along through here. But notice there's a little bit of a pattern going on. So maybe, just maybe, Milankovitch had something here in explaining the ice ages, why the ice ages happen, using these astronomical theories, using the tilt of the Earth, the precession, the eccentricity of Earth's orbit. Maybe those have something to do with it. Maybe those cycles, those natural cycles in Earth's history, have something to do with the ice ages. Isn't that wild? That's the ice ages. There are many theories to explain why we have them. The Milankovitch theory uses Earth's relationship with the sun to explain it, going on the idea that different amounts of solar radiation can cause climate changes. That's been today's digital replay. If you have questions, comment below, send me an email, or see me in class. We'll see you next time.